Here we have a question dealing with electronic circuits, that is under section 4, electromagnetism. Let's take a look. Figure 7.1 shows a circuit diagram that includes component X. Here we have a depictive circuit diagram. The passive electronic components include component X, a 30 ohm resistor, a 20 ohm resistor, and an ammeter, which measures the value of current. The active component in this circuit appears to be a battery, which is also connected to a key. Now we are asked to name the component X. From the symbol used to depict component X, we understand that the thermistor is the component that they are talking about. So component X is a thermistor. Moving on to part B, the electromotive force, that is the EMF of the battery, is E. Let's depict it as such, E. The switch is now closed. When the switch is closed, it is evident that they are indicating to us that current I starts to flow in the circuit. The potential difference, that is PD, across the 30 ohm resistor is V30. So here we assume an imaginary voltmeter measuring the value of voltage. Apologies, measuring the value of voltage across this component to be V30. Consequently, since the 30 ohm resistor and the thermistor seem to be parallel to each other, the terminals across which we measure the voltage for the 30 ohm resistor are the exact same terminals where we measure the voltage across component X. So component X also has its voltage V30. The potential difference across the component X is Vx. Since we just understood that the terminals for the thermistor and the terminals for the resistor 30 ohm are the same, the voltage measured across both those points will evidently be the same. And thus we conclude that Vx is nothing but V30. Moving on to the next part, they are also asking us the relationship between E and V20. E is the voltage measured across the terminals of the battery, or in other words, the voltage supplied to the operation of the entire circuit. V20, however, is the voltage measured across these two terminals, V20. So indicating that the voltage across these two terminals is V30 and the voltage between these two terminals is V20 and the voltage across the entire circuit is E. We understand that this terminal A, let's call it, is nothing but this terminal, that is terminal C, and this terminal, that is terminal B, is nothing but the same terminal B. So in other words, the total voltage measured across AB, that is E, must be equivalent to the total voltage measured across CD. The total voltage measured across CD is the addition of V30 or Vx and V20. Since V30 is nothing but Vx, we substitute and rewrite the equation as Vx is equal to E minus V20. So here we have the equation in terms of Vx as indicated. Moving on to the next part, the EMF of the battery is 6 volt and the resistance of component X is 15 ohm. Calculate the total resistance. Here, before we calculate total resistance, let us recollect the formulas for series and parallel combination of resistors. When resistors are in series, the equivalent resistance Rs is given as R1 plus R2. When resistors are in parallel, we have two variations of formulas that could be used. 1 by R parallel is equivalent to 1 by R1 plus 1 by R2, or we could use this other formula. R parallel is equivalent to R1 times R2 divided by R1 plus R2. This is the same formula as the previous one, except we have rearranged and written in terms of R parallel instead of 1 by R parallel. The two components, that is the 30 ohm resistor and component X, appear to be parallel to each other. So their equivalent resistance can be found out as R equivalent of component X and 30 is equal to 30 times 15 divided by 30 plus 15. We simplify as such. And get the value to be 10 ohm. So this equivalent combination of component X and 30 ohm, which has an equal resistance of 10 ohm, is finally in series with the 20 ohm resistor. And the total resistance, R total, is the equivalent combination of 15 and 30, giving us 10 plus 20 ohm. So we get the final value of resistance to be 30 ohm. The ammeter reading. The ammeter is seen to be measuring the total current I in the entire circuit. The ammeter reading I can be found out as the total voltage supplied E divided by the total resistance. Here we notice the battery is of EMF 6 volt and R total has already been calculated. So current reading I is 6 divided by 30, which is exactly equal to 0.2 ampere. Now this answer comes with an assumption that the ammeter is an ideal ammeter which does not offer any resistance. Moving on, the temperature of component X increases. State and explain what happens to the ammeter reading. We understand that specifically for a thermistor, the resistance is inversely proportional to temperature, which indirectly tells us that an increase or a rise in the value of temperature results in a decrease in resistance. And since there is a decrease in resistance, the ammeter reading will increase. So a decrease in the resistance for component X results in an increase in the ammeter reading. So finally, the ammeter reading increases due to the resistance of component X decreasing as a consequence of temperature increasing. This concludes the solution to this question. Thank you.